Welcome back, everyone. The crust beneath our feet hides a form of energy so dense it can outlast all the fuels humanity has ever burned. It's not a fantasy, it is heat. At several kilometers down, the temperature of the rock surpasses 400 degrees Celsius, enough to generate supercritical steam that carries 5 to 10 times more energy than the water vapor used in today's geothermal plants. Unlocking that reservoir requires new drilling physics, materials that survive extremes, and a complete redesign of the power cycle itself. Please subscribe now. To reach a superhot reservoir, engineers first calculate the thermal gradient of a region, the rate at which temperature rises per kilometer. In volcanic zones such as Iceland, Japan, and parts of the American West, the gradient can exceed 100 degrees Celsius per kilometer. At that rate, temperatures above 400 degrees Celsius can occur at depths of only 4 to 5 kilometers. Ordinary oil field rigs can reach those depths, but the challenge is not drilling that far. It is drilling into rock that behaves more like glass than granite, where temperatures melt steel and destroy lubricants in minutes. Conventional rotary bits rely on weight and torque to crush rock with hardened teeth. At 400 degrees Celsius, the steel softens, the bearings fail, and the drilling muds designed to cool the bit boil instantly. To go deeper, researchers are turning to non-contact drilling, methods that rely on energy, not mechanical force, to remove material. The most promising among them is millimeter wave plasma drilling. Imagine a beam of electromagnetic energy much like the microwaves that heat food, but concentrated into a pencil-thin column of power. When that energy strikes rock, it excites the molecules, driving rapid expansion that fractures the surface. A plasma zone forms, an ionized layer that absorbs even more energy, creating a self-sustaining tunnel of superheated gas. Unlike conventional drilling, there are no bits to wear out. The rock itself is converted into gas and micron-scale dust that can be removed with a steady flow of inert gas. The physics behind it rely on dielectric loss and resonance. Most igneous rocks contain silicates with polar bonds that respond strongly to electromagnetic fields at specific frequencies, typically around 30 to 300 gigahertz. By matching the frequency to the rock's permittivity, the system heats the material volumetrically rather than just at the surface. In laboratory tests, this method produces penetration rates up to 10 times faster than mechanical drilling through basalt. The beam can reach temperatures above 2000 degrees Celsius at the focal point, which is enough to vitrify the borehole wall into glass, sealing it against collapse. To deliver that energy downhole, engineers use waveguides, metallic tubes that transmit millimeter wave power from a generator at the surface to the plasma zone kilometers below. The waveguide is cooled by a continuous flow of nitrogen or helium gas, keeping its internal walls near ambient temperature, while the beam at its center reaches thousands of degrees. Advanced ceramic coatings line the tip to resist erosion. The plasma itself forms within a pressure-controlled chamber at the bottom, where sensors measure reflection coefficients to adjust beam focus and maintain optimal coupling with the rock. The greatest obstacle is efficiency. Generating multi-megawatt millimeter wave power requires gyrotrons, large vacuum tubes originally developed for nuclear fusion research. Each gyrotron can produce several megawatts of continuous power with electrical efficiency around 50%. To drill economically, the system must convert as much of that energy as possible into rock removal. Current prototypes achieve about 70% coupling efficiency, meaning most of the power goes into vaporizing rock rather than heating the surrounding formation. Once the borehole reaches target depth, the challenge shifts from drilling to containment. At 400 degrees Celsius and 250 bar, water enters a supercritical state, neither liquid nor gas, but a dense, highly mobile fluid. Its enthalpy is immense, containing roughly 5 times the usable energy per kilogram of standard geothermal steam. Extracting that heat requires tubing, pumps, and surface equipment built from nickel-chromium alloys that resist creep and oxidation far beyond the limits of stainless steel. A superhot well operates in cycles. Cold water, or in some designs carbon dioxide, is injected down one well and returns through another as supercritical fluid. Because the density and viscosity of supercritical water change dramatically with pressure, Flow control is absolutely critical. Engineers model the reservoir using computational fluid dynamics to predict convection loops, ensuring that the circulating fluid does not cool the rock too rapidly. The goal is to sustain a temperature above 400 degrees Celsius for decades. When the fluid emerges at the surface, it passes through a two-stage expansion system. In the first stage, the supercritical water expands through a turbine designed for dense fluid, driving a generator. The exhaust then flashes into steam for a conventional secondary turbine. This hybrid cycle captures both the kinetic and latent heat components, pushing thermal efficiency beyond 50%. Conventional geothermal plants rarely exceed 20%. At such high temperatures, materials science becomes the silent enabler. Every joint, valve, and casing must survive chemical attack from silica, sulfur, and dissolved metals. Engineers rely on alloys such as Inconel 718, Hastelloy X, and oxide dispersion, strengthened steels that maintain structural integrity past 700 degrees Celsius. Ceramic composites are now under test for the hottest zones. Sensors made from sapphire optical fibers monitor pressure and temperature in real time, unaffected by electromagnetic interference or heat. The drilling phase is only the beginning. Heat management within the reservoir determines whether the project is sustainable. Over time, the rock cools, and if water flow is too fast, thermal fractures can seal or propagate unpredictably. To prevent this, operators pulse the injection rate, creating breathing cycles that allow the rock to re-equilibrate. Seismic sensors placed in surrounding boreholes detect micro-fractures, giving feedback on stress evolution. One of the most fascinating aspects of superhot systems is self-sealing vitrification. As plasma drilling melts the rock, the glassy layer lining the borehole can prevent unwanted fluid loss into surrounding fractures. Traditional geothermal wells often lose up to 50% of injected water due to permeability. By vitrifying the inner wall, losses drop to near zero, allowing a closed loop with higher pressure stability. This is the first time a drilling method creates its own casing out of native material. Cooling and restarting the plasma drill require precise control. After each energy pulse, the chamber pressure is vented through filters that capture vaporized silica dust. Sensors measure beam attenuation to ensure the plasma remains stable. If the reflection signal spikes, it indicates the formation of a melt bubble, prompting automatic power modulation. This closed-loop control allows continuous operation without human intervention deep underground. From a thermodynamic perspective, a superhot well effectively becomes a heat engine coupled directly to the earth. The hot reservoir serves as the high-temperature source, and the injected fluid provides the working medium. Because the temperature difference between reservoir and surface is so large, the Carnot efficiency ceiling is far higher than in standard geothermal. For a 400 degrees Celsius source and 30 degrees Celsius sink, the theoretical maximum is around 55%. Actual systems may reach 45 to 50%, rivaling modern combined cycle gas turbines without burning any fuel. Economically, the drilling cost dominates early investment. Mechanical drilling can cost over $10 million per kilometer in hard basalt, but plasma drilling could reduce that by half by eliminating bit wear and tripping delays. Each gyrotron module is reusable. Once a hole is complete, the equipment moves to the next site. Over multiple wells, energy cost per megawatt hour could fall below that of fossil fuels, provided the system runs continuously for 20 years or more. Thermal drawdown remains a concern. Unlike shallow geothermal fields that rely on convective reservoirs, superhot wells tap conductive heat from solid rock. Engineers must estimate how quickly the rock cools and how far heat can flow laterally from surrounding formations. Numerical models show that a 5-kilometer deep, 400 degrees Celsius reservoir can sustain production of 50 megawatts for several decades before temperature declines significantly. Repressurizing the reservoir with cooler fluid can extend life even longer. Scaling this technology depends on drilling automation. Each plasma system is guided by sensors and AI algorithms that interpret acoustic and electromagnetic feedback to steer the beam. Because the plasma is invisible to cameras, software infers progress by measuring impedance changes along the waveguide. Real-time adjustments keep the bore vertical or angled as needed for multi-well arrays. When combined with surface robotics for pipe handling and module alignment, a single team can supervise multiple drilling rigs simultaneously. The environmental profile of superhot geothermal is remarkably clean. The closed-loop design prevents fluid venting, and the high temperatures destroy most chemical contaminants. Land footprint per megawatt is smaller than wind or solar, and output is continuous, day and night. Cooling water use is minimal because expansion turbines can be air-cooled. Unlike traditional hydrothermal plants, no large brine ponds or re-injection networks are required. Even the waste heat from drilling can be recycled. The nitrogen or helium gas that's used to cool the waveguide exits at several hundred degrees, and this can preheat the incoming water for the next stage, which improves the total system efficiency. Engineers are experimenting with regenerative heat exchangers made of ceramic honeycomb structures that store and release heat during the operation cycles. Once multiple wells are established, they can connect through a subsurface heat grid. By interlinking several boreholes within a few kilometers, heat extraction becomes balanced across a wider area, which reduces local cooling and extends the field life. Each production well can feed a dedicated generator or link into a shared supercritical steam loop. The modular nature of these systems makes them ideal for scaling from demonstration all the way up to hundreds of megawatts. Instrumentation plays a key role in maintaining safety. Fiber optic strain gauges detect casing deformation, while acoustic sensors monitor for gas pockets or rock movement. Automated valves can isolate sections instantly if any anomalies appear. At the surface, digital twins simulate every thermodynamic variable, enabling predictive maintenance rather than reactive repairs. From an educational perspective, this technology unites multiple physics domains: electromagnetism, thermodynamics, materials science, and control theory into a single system. It demonstrates how mastery of energy transmission at millimeter wavelengths can open an entirely new energy frontier. Plasma drilling, once confined to research laboratories, is becoming an industrial process with clear metrics and reproducible performance. If successful, superhot rock drilling could redefine baseload power. A single site could supply clean electricity for centuries using nothing but the Earth's internal heat. Because the energy density of a supercritical reservoir is measured in tens of gigawatts per cubic kilometer, only a handful of wells would be required to power entire regions. Unlike wind or solar, output is unaffected by weather or daylight. Future improvements may involve hybrid systems, combining plasma drilling with resonant mechanical hammers to clear debris faster, or to shape boreholes of varying diameter. Research is also underway to use carbon dioxide lasers for initial pilot holes, creating channels that guide millimeter wave beams more precisely. Integration of superconducting waveguides could raise efficiency and reduce power loss during transmission. Every technological revolution begins with solving one stubborn limitation. For geothermal power, that limitation has always been temperature. By moving beyond the 200 degrees Celsius barrier that defines traditional systems, humanity enters a realm where the Earth itself becomes a near inexhaustible power source. Achieving it requires courage to drill deeper, patience to refine plasma control, and the precision of both physics and engineering working in harmony. The story of superhot rock drilling is not one of science fiction, but of physical law applied at unprecedented scale. Energy is everywhere below us, waiting behind a few kilometers of stone. The tools to reach it, gyrotrons, ceramics, and optical sensors already exist. What remains is the determination to build, test, and learn from the depths. Thank you very much for watching. Please like and subscribe.